Hello, everyone. In previous lessons, we have discussed the development, classification, and basic structure of industrial robots, gaining a preliminary understanding. We have also learned that industrial robots are intelligent devices capable of flexible movement, primarily used to replace humans in performing precise movements and tasks in specific scenarios. Industrial robots possess various coordinate systems as needed, and users can call upon the appropriate coordinate system as required. Now, let's learn about the coordinate systems of FANUC robots. First, understand the types of FANUC robot coordinate systems. FANUC robots have two main categories of coordinate systems: joint coordinate systems and Cartesian coordinate systems. The Cartesian coordinate system is further divided into world coordinate systems, manual coordinate systems, user coordinate systems, and tool coordinate systems. Next, let's introduce the characteristics and functions of these coordinate systems one by one. 1. Joint coordinate system. The joint coordinate system defines the coordinates corresponding to the movement of each joint. When the robot is in the joint coordinate system, each joint moves independently during debugging, as shown in the figure, which illustrates the robot's movement direction in the joint coordinate system. Each joint will have a corresponding independent coordinate value relative to the origin of the joint coordinate system during movement. As shown in the figure, the coordinate values correspond to the coordinates of each axis of the robot in its current posture. It should be noted that these coordinate values refer to the robot's mechanical origin. The manufacturer has predefined and set the position of the mechanical origin before shipment. If the mechanical origin is lost, refer to the markings on each axis for setting, as shown in the figure for the first and third axes. The manufacturer's default mechanical origin markings are displayed. The remaining 4 axes have similar markings at their respective positions. If the mechanical origin is lost, reference these markings to set the mechanical origin. 2. Cartesian coordinate system. In the Cartesian coordinate system, the position and posture of the robot are defined by the coordinates from the origin of the Cartesian coordinate system in space to the origin of the Cartesian coordinate system on the tool side, including x, y, z coordinates and the rotational angles around the relative x, y, z axes of the Cartesian coordinate system in space, w, p, r. 1. World coordinate system. The world coordinate system is a standard Cartesian coordinate system fixed at a predetermined position of the robot. It can be used for manual operation, general movement, and handling scenarios involving several robots or external axes, and is the default coordinate system for the robot. The origin is defined as the intersection of the axis lines of the J1 and J2 reducers, with the z-axis perpendicular to the ground and pointing upwards, the x-axis pointing forward from the robot, and the y-axis determined by the right-hand rule, as shown in the figure. This diagram illustrates the coordinate values of tool center point 2 relative to the world coordinate system. 2. Manual coordinate system. The manual coordinate system is a Cartesian coordinate system defined for effectively performing Cartesian job movements in the work area. This coordinate system is used only as a manual feed coordinate system and has no special significance for its origin. If not defined, the world coordinate system will replace it. 3. User coordinate system. The user coordinate system is a Cartesian coordinate system defined by users for each workspace. It is used for teaching and executing position registers, executing position compensation commands, etc. If not defined, the world coordinate system will replace it. The user coordinate system is defined by the coordinates of the origin, x, y, z, and the rotational angles, w, p, r, of the x, y, z axis relative to the world coordinate system. Up to 9 user coordinate systems can be set. User coordinate systems are typically used on work planes different from the world coordinate system, making it convenient for users to calibrate points. As shown in the figure, the workpiece plane on the table does not align with the robot's world coordinate system. Therefore, setting a user coordinate system allows the coordinate system to be on the same plane as the work surface, facilitating the calibration of robot trajectories and work points. For tool coordinate system, the origin of the tool coordinate system is generally the center point of the flange on the 6th axis of the industrial robot. Once the tool coordinate point and its coordinate system are successfully set, the coordinate values relative to the world coordinate system and the user coordinate system will be determined in space. The coordinate values of other coordinate systems are also relative to the current tool coordinate point. Therefore, different tools have different tool coordinate points and corresponding coordinate values. FANUC robots can set multiple tool coordinate systems, but the tool's working point is generally set to the center of the 6th axis flange upon shipment. As shown in the figure, the teaching pendant tool coordinate setting screen shows 10 tool coordinates. But their corresponding x, y, z values are all 0, indicating these tool coordinates have not been redefined and are in the default position, the center of the 6th axis flange. After setting, the tool coordinate point of tool coordinate 1 is set to the tip of the welding torch, and the values of tool coordinate system 1 have changed. We continue to learn about moving the robot in the joint coordinate system and world coordinate system. The joint coordinate system and world coordinate system are the most commonly used methods for moving robots. 1. Steps and methods for moving the robot in the joint coordinate system with the teaching pendant. Specific requirements: use the teaching pendant to move the robot's 6 axes in positive and negative directions. The steps are as follows. 1. Power on the robot system and set the mode switch on the robot control cabinet to T1 mode. 2. Set the auto run switch on the teaching pendant to ON. 3. Restore the robot posture to J1 to 0, J2 to 0, J3 to 0, J4 to 0, J5 to -90, J6 to 0. 4. Press the chord key on the teaching pendant, the coordinate system switch key, until the teaching pendant is in joint coordinate mode. 5. Simultaneously press the enable key and shift key to power on plus move each axis. 6. As shown in the figure, in the joint coordinate system, you can press the POSN key on the teaching pendant to select joints and observe the robot's position value changes in real time. 2. Steps and methods for moving the robot in the world coordinate system with the teaching pendant. Specific requirements: use the teaching pendant to move the robot in the positive and negative directions of X, Y, Z axes. The steps are as follows. 1. Power on the robot system and set the mode switch on the robot control cabinet to T1 mode. 2. Set the auto run switch on the teaching pendant to ON. 3. Restore the robot posture to J1 to 0, J2 to 0, J3 to 0, J4 to 0, J5 to -90, J6 to 0. 4. Press the chord key on the teaching pendant, the coordinate system switch key, until the teaching pendant is in the world coordinate mode. 5. Simultaneously press the enable key and shift key to power on plus move each axis of X, Y, Z. 6. As shown in the figure, in the world coordinate system, you can press the POSN key on the teaching pendant to select a world, and observe the robot's position value changes in real time. In this lesson, we learned about the basic coordinate systems of industrial robots. Mastering the basic coordinate systems of industrial robots lays a solid foundation for subsequent learning. Lastly, please complete the following exercises. See you in the next lesson.